All right, we're going to do AP Physics 1. I hope this takes a lot less time than Physics C does. At least it's not two sets of it. All right, a reminder that this is brought to you by World's Finest Physics. So, World's Finest Physics, we're holding a non-endorsed by anybody but me Summer Institute for all physics teachers, July 18th to 21. It's in Frisco, Texas. The topics that it aligns with are the mechanics, P1, C mechanics stuff. If you're interested, more information or to register or to reach out to me, findphysics.com. All right, let's see what we got going on here. I haven't seen this before. So I'm doing this cold, so just that's your fair warning. Two blocks are connected to string passing over the pulley. Block one horizontal surface attached to springs on stretched length. All right, frictional forces are negligible. Ooh, that's nice. The pulley's axles become a rock blocking the surface. Block two is released from rest and moves downward before momentarily coming to rest. And then they do this thing on P1, which is weird. I don't know if they're doing it P2. They don't do it in C. Where they it's like a bulleted list of the variables. Okay, whatever floats your boat. All right, block two starts from rest and speeds up. Hold on a second. Okay. Yes. All right. Then it slows down and momentarily comes to rest at a position below its initial position. In terms of only the forces directly exerted on block two, explain why block two initially speeds up and then why it slows down momentarily to a stop. So I'm going to say this. I'm going to say that before equilibrium, you've got mg and you've got kx. And then after equilibrium, I'm going to say that you have mg. I'm going to say you have like kx. So I'm going to say before reaching equilibrium, the down mg is greater than the up kx. So the downward velocity speeds up. And then after that, kx is greater than mg, so the v slows down. Okay, so that's my answer to that. Derive an expression for the distance, delta y, that block two travels before momentarily coming to rest. Okay, so the key markers here are distance and a speed, which is rest. So to relate distance and speed, we use energy. So this is how I know it's energy time, is because you're not saying anything about time or force or anything like that, or acceleration. If it's just a distance and a speed, which is what these two things are, the distance is in the potential energy and the speed's in the kinetic energy. Well, the deal here is that gravitational potential energy becomes spring potential energy. Now, you got to watch out because there's two different masses, so I have to be very clear about which mass I'm talking about. Here, M2 descends a distance delta y. M1 does not change the gravitational potential energy. That becomes 1/2 k delta y squared. That's the same distance. That is the same distance as the stretch. So I can nuke one of the delta y's, and then I can delta y equals 2 mg's, m2g's over k. Make sure you say which m it is. If they have subscripts, put subscripts. All right. Now, indicate whether the total mechanical energy of the block spring earth system, it does not change. Briefly explain your reasoning, because the only energy transfers occur between gravitational potential energy and spring potential energy and kinetic energy, and all three energies are included in this system, right? There's the earth is in the system, so we have UG. The spring is in the system, so we have the blocks are in the system, so we have the kinetic energy, right? So all these energies go to the system. There's no unbalanced external forces on this system that are external to this system. There's no energy dissipation by force friction. This is what do you want to hear? I don't know what's on the rubric, so I'm going to put down everything I know. All right. Oh, it still goes. Spring the earth both blocks and the string, but not the surface. Let the initial state when the blocks are at rest just before they start moving. Final state is when the blocks first come momentarily to rest. A is a bar chart, represents the energies in the scenario where there's negligible friction between block one and the surface. Okay, spring and gravitational energy, spring and gravitational energy. Okay, sure. Okay. Let's see. Complete diagram B for the scenario in which friction is not negligible. The energies for the initial state are already provided. Well, you're going to have some spring energy, but you're not going to have as much. You're not going to have as much spring energy because, well, let's see. Yeah, because the spring isn't going to stretch as far. So spring is not going to stretch as far because friction is not going to let it move as far. Okay. But then the block is not going to fall as far. The block is not going to fall as far. So the block is still going to have some potential energy relative to here. So the block still has some potential energy because it doesn't fall as far. The spring doesn't stretch as far, so the block doesn't fall all the way down to zero, but you still need to dissipate some energy. Did I? 1, 2, 3, 4. I did not. Okay, so what I'm going to do is, first of all, do everything in pencil. The second thing I'm going to do is I'm going to say no, and I'm going to do maybe like that right there. And I'm going to maybe make a note to the reader that says, spring doesn't stretch. Maybe I can do that down here. Whatever, it just stretches far. So less US. Block doesn't fall all the way to zero. So there's still some UG, and the total is less because energy is dissipated to or by force friction or whatever it is you want to say. Okay, finally, we're on number 2. All right, so we've got a planet and 2 moons. Moon A and Moon B, they're identical. It's convenient. The mass m0 of each moon is significant, but less than the mass mp of the planet. At some point in their orbits, the planet and the 2 moons are aligned as shown in the figure. Let's make the planet be like green, and let's let the moons be, I don't know, blue, and then the other moon can be red. Okay, so the 2 moons, when they have the location shown in the figure on each dot, draw and label forces. So on Moon A, you have a force of gravity from Moon B, and you also have a force of gravity from the planet. And on Moon B, you have a bigger force of gravity from the planet because it is closer to the planet, but you also have some force of gravity from Moon A. Okay. Consider the net gravitational force exerted on each moon due to the planet and the other moon. Justify why the magnitude of the net force on Moon A could be larger than B. So why could this force be larger on Moon A? Well, B has 2 rightward forces, okay, adding to a large F net to the right, whereas A has force to the left, which subtracts from the F net. Okay, that makes sense to me. All right, justify why the magnitude of the force on Moon B could be bigger. Oh, because it has a bigger force gravity. So force gravity from the planet on A is greater, so that might cause greater F net on A than on B. Okay, derive expressions for the following quantities. The net force on Moon A, so the net force on Moon A is going to be 2 forces in the same direction. G, m0 and m0. Okay, so that's m0 times m0 over the distance from A to B, which is going to be RA minus RB all squared. We're going to add to that the force from the planet, GM naught MP over, let's call this F net on A, equals, okay. Let's say derive. I didn't really derive. I just kind of wrote it. So I might go back and put some extra work later. Is this RA squared? Okay, so I might put some work later. Each moon has 2 GMM over R squared forces on it from the other moon and the planet, right? And so for moon A, add, right, both forces are in the same direction, right? Okay, and then here I'm going to say F net on B. That's going to be the difference. So you're still going to have GM naught MP over RB squared, but you're going to have G M naught M naught. I don't know why I put a parentheses over RA minus RB squared. So I'm going to say this force is to the left, so negative. This force is to the right, so positive. Again, it says derive. You want to show some kind of work. Okay, could the expressions in part C support your reasoning in B1? What's B1? B1. Moon A could be larger than the magnitude of B. I'm going to say yes. Explain my reasoning. Okay, so I'm going to say, okay, so F, force on A, GM naught squared over RA minus RB squared plus GM naught MP over RA squared. Okay, and then I'm going to write the other one. I'm going to say force B equals GM naught squared over with a negative RA minus RB all squared, right? Plus GM naught MP, watch the box, over RB squared. And then what am I going to say? I'm going to say the force on A could be larger because both terms are positive, whereas for B, there is a negative term, right? Okay, could the expressions in part B support your B2? What was B2? Force on B could be yes, and I'm going to say okay. The GM/MP over RB squared term is bigger than GM naught MP over RA squared, since RB is less. So this could overcompensate for the negative force A exerts on B. All right, there's your quantitative translation question. All right, now for the experimental design. A wheel is mounted on a horizontal axis, light string attached to the wheel's rims, wrapped around several times. Small block attached to 3 inch to the figure. When the block is released and rest begins to fall, wheel rotates. 2 students are discussing how different forms of energy change as the block falls. One student says that the kinetic energy of the block increases as it falls. Sure. The second student says that this is because the gravitational potential energy is converted to kinetic energy. The students decide to test whether the decrease in gravitational energy is equally increased in kinetic energy, which it won't be, because some energy is going to go to the wheel's rotation before it reaches the floor. Okay, design an experimental procedure the students could use to compare increase of blocks translated to a decrease in the table list quantities. Okay, so I might say height, the block falls. I'm going to call that H, and the equipment would be a meter stick. Okay, and then the time, the block. Seriously? Do you just, I mean, there's like no space to put it. Stupid. Okay, stopwatch. Okay, describe the overall procedure. Reduce experimental. Okay, so release the block from a known height H to measured by the meter stick. Okay, right. Measured by the meter stick. Use a stopwatch to time how long it takes the block to reach the floor. Perform 100 trials with the same H. And what are we going to do? We're going to average all the T's measured. Okay, so how could the students could determine the kinetic energy immediately before it reaches the floor? All right, so kinetic energy is 1/2 mv squared. Oh gosh, I need to measure the mass of the block too. Mass of block, m, scale. Okay, so put the block on the scale and get its mass. Okay, now how am I going to get the speed? Well, here's how you get the speed. So it turns out that if you just do height over time or any length over time, that's average velocity, right? But average velocity is also initial and final velocity literally averaged together. The initial velocity is 0, so the V final, is going to be 2 height over time. So use V equals 2 height over time to get the final velocity at the floor, okay? Then use K equals 1/2 mv squared to get the final kinetic energy of the block. All right. Kinetic energy gained by the falling block. Change in gravitational energy of the block or system. The graph above represents both the change in gravitational potential energy of the block system and translational kinetic energy. On the graph, draw a line or curve to represent the rotational kinetic energy of the wheel. Okay, so the amount of potential energy you lose has to equal the amount of kinetic energy you gain total. So here, if you lose 0.3 and you gain 0.1, you had to gain 0.2 of rotational kinetic energy. Did say it didn't say label it, but I am going to use a straight edge because I want to be really nice looking, right? Okay, so there you go. The students also measure the angular velocity of the wheel. As the block falls, determine the rotational kinetic energy of the wheel. Students then make a graph of that, draw the best fit line. Okay, maybe a few points above and below. I don't know that I did a good job of that. Maybe I don't care. Using the line you drew, calculate experiment with rotational inertia. Okay, so rotational kinetic energy is 1/2 I omega squared. So K rotational over omega, that's rise over run. So on the other side, 1/2 I, that's got to be the slope. So what is the rise over run of this thing? Where'd my calculator go? Oh, here it is. Okay, so let's take a couple of points there. So that's 0,1. And sure, 40 comma, what is that? 1.16. Sure, why the heck not? All right, so slope is going to be, for me, 1.16 minus 0.1 over 40 minus 0. So 1.06 over 40. 0.0625, so slope is 0.06. This is 265, I meant to say, and that's equal to 1/2 of an I. So if I double that, then I get the full I. The I is going to be 0.053 kilogram meters squared. All right, are we done now? Thank goodness. Okay, it's this again. It's the sticky bouncy collision. I'm not even going to read it. I'm going to skim it really quick. All right. This is the momentum of the clay block system immediately after the collision. The momentum of the sphere block system has got to be the same, doesn't it? Because they're both the same mass at the same speed. Same mass, same speed, same momentum. Okay. Whatever. All right. After the clay block A lands horizontal distance from the edge of the table. Does block B land on the floor greater distance? All right, here we go. It's time for ABCD. A, answer the question. B goes a greater distance. All right, A, answer the question. B, what's some basic physics that's involved? How about the fact that momentum is conserved in both collisions? That's some basic physics. That's always going to be true. Momentum is conserved. Also, since both tables have the same height, okay, both blocks spend the same time as projectiles, right? That's delta height equals 1/2 gt squared. Same. Okay, so that's some basic physics. What's some connecting to this problem here? So I'm going to connect this problem. I'm going to say if the ball bounces back, it has negative momentum after the collision. Okay. So box B, is it a box or a block? Oh, it's a block. I don't even care. Has more positive velocity than A to compensate for the ball's negative momentum. Okay, so there we go. I talk so connect to this situation, answer the question, basic physics, which could include equations. So here I could have said m ball v ball initial equals m ball v ball final plus m block v block final. I could have said, well, if this is positive and this is negative, this has got to be like a big positive, right? Okay, well, that's kind of more C, which is connecting. It doesn't matter. Just I teach my students, make sure you've answered the question, make sure that you've said some basic physics, which might include an equation, probably does, and have you connected this problem. C could also be compare and contrast. So like they both have the same momentum, compare, but B has more block velocity after. Contrast, say what's different. Say what's different how, what quantities are different how, compare, contrast, say what's the same, compare. Okay, so now I'm going to D, draw my ideas back to my answer. I'm going to draw my ideas with if B has faster speed and spends the same time in the air, B goes farther. And I might just throw a little equation there for that. X equals V naught T, like the horizontal projectile motion equation, right? Okay. The spring of unknown spring constant attached to a ceiling. The lightweight hanger is the lower end of the spring. Motion detector is placed on the floor facing upward. Okay. 50 kilograms placed on the hanger, allowed to come in an equilibrium position. The spring is then stretched. Distance D naught. Records the height of the hanger as a function of time. Okay, so we get a graph looks like this. Calculate the spring constant. There are two ways to do it. So one way to do it is to just say that at equilibrium, Kx equals mg. Okay, so what is the equilibrium stretch? It used to be 0.1. Does it say that the lightweight hanger? Okay, that's important. The hanger doesn't have its own mass. Okay, so it was 1 meter. Now it's 60 centimeters. So that means that this is 40 centimeters of stretch. The mass was 0.5. So 0.5, go ahead and use 10. So 5 over 0.4, I should do that in my head. 12.5 K is 12.5 newtons per meter. That's one way to do it. The other way to do it is to say T is 2 pi radical M over K. So if I square, what is the period here? The period is 1.25. So 1.25 squared equals 4 pi squared times 0.5 kilograms over K. All right, so 4 pi squared is basically 40. So I'm going to take my 1.25 squared, divide by 40, because pi squared is basically 10. I get this ugly number, and then I need to do 0.5 divided by that ugly number, and I get 12.8. Okay, so my K is going to be 12.8 newtons per meter rather than 12.5. I've written this problem several times, and I can make it come out exactly the same both ways. People who write this problem don't care that much, and I'm allergic to all this spring shit. Stop. All right. Time that the object spring Earth system, that's everybody, has a total kinetic energy, sure, and a total potential energy, whatever, at 1.13 seconds. Where am I going to find that? 1.04, 1.08, 1. Okay, right there. It again has the same kinetic potential energy Explain how a feature of the graph indicates the total kinetic energy is the same both these times. I'm going to say kinetic energy equals 1/2 mv squared. I'm going to say the mass stays the same. So it's the same kinetic energy if the speed is the same. So we're going to look and see if the slope is the same at both points. Okay, the music is playing. That means I need to finish this up. All right, so here we go. Briefly explain why the total potential energy is just the same at both these two times. I'm going to say it's the same distance from equilibrium. Or you could also just say we know E equals K plus U is constant. So same K, same U. All right, and then what are the U is 1/2 kx squared, right? It's always good to say an equation anytime you explain anything. All right, the experiment's repeated with the spring constant 4 times as much, same length as the original, the same mass. Determine the new equilibrium position. Okay, well, kx equals mg. So if k is 4 times as much, right, the x is 1/4 as much, or 10 centimeters. So new position is 90 centimeters. The objects again pull down the same distance on the following graph. Draw a curve representing the motion. Okay, so here's what I know, that this is going to be 90 centimeters. We know that t equals 2 pi radical m over k. And if the k is multiplied by 4, the period is going to be half as much. So I need to make a period 85, 95. All right, so I need to make the period half as much. So it used to be 1.25. Good grief. What is 1.25 divided by 2? That's 0.625. Sure. I hope it's right there. Okay, and then 1.25 again. And then what's that plus 1.25 is 1.875. Sure. Okay, and then what's 0.625 divided by 2? Oh my gosh. I don't know if I can actually eyeball this. Okay, maybe there, maybe there, maybe there. Okay, here we go. Good luck, everybody. All right. End of exam. All right. My favorite 3 words. All right. Peace out. Tomorrow it's going to be Physics 2.